So in this video, we're going to be talking about random variables for the continuous type. So we've been discussing probability mass functions for random variables that are discrete random variables that take on discrete, say, integer values, typically, but discrete values, so we don't have intervals of possibilities. However, many situations involve intervals of data. So for example, time until a light bulb fails. Well, time is infinitely divisible. It's an interval of times a light bulb could possibly last. Finishing time in Boston Marathon participants, that again is continuous data because time is infinitely divisible. Lengths of things like narwhal horns. Length is infinitely divisible because you could have a length of a horn saying 10.5 inches or 0.65 meters. Those kinds of things. So let's talk about x being a random variable of this particular type, of continuous type. Well, if we talk about the probability that we're exactly equal to one of these values, that is always going to be 0. So we're not going to be talking about a probability mass function anymore because we're not going to have the probability of x equaling a specific value because, again, the possibility that you select a number at random and guess what that number at random is, if it's from a continuous set of data, it's always going to be 0. So we have to do something a little bit different. But let's try to see if we can estimate some of these probabilities. So first we're going to make a relative frequency histogram. What we mean by that is the areas of the rectangles are going to represent the probability that we fall between two endpoints. So here's an example. So what this means is that, say here, if we fall between, this looks like what, 0.6789, so 0.9 to 1.1, so something that falls in that range, we're going to estimate by being about 0.6 here. Okay, that's what we mean by the areas. So the area of this rectangle, though, the height of this rectangle is 0.6, the base is 0.2. So we would multiply those together and get the area here, estimating the probability that we're between 0.9 and 1.1 in this case. So these areas here are going to end up adding to 1 if it's going to be a probability function. Okay, so let's choose that f of x. So going back a screen here, choose that f of x here that goes through those rectangles. So that's what I mean by choosing f of x so the rectangles fill in the area under that curve. Well, as we get more and more rectangles and go into that function, then we know that we're going to get more and more rectangles is going to approach the area under the curve. So then we know that the probability that an estimate falls between those two, probability of the measurement, sorry, falls between those two values is the integral of this function. Okay. So we're going to refer to this f of x as the probability density function of x. So instead of giving a mass to a particular point, we're going to give a density to a particular curve to be able to figure out its probability by looking at area underneath it. So we're going to say that x is a random variable of a continuous type with support s and probability function f of x if we have the following characteristics met by our function f of x. So first, just like before, our density function is going to have to be positive for x on the support. When we do the integral over the entire sample space, so I'm going to write it as minus infinity to infinity, in this case, that integral is going to be 1. And if we have a subset, an interval that's a subset of our sample space, our support I mean, then the probability that x falls between those two values is the integral. So this all is analogous to probability mass functions, right? We know that the probability mass function, no matter what we plug in for x, we better be positive if it's in the support. We know that if we sum up over the support, we have to get 1. And we know that if we have values in the subspace, in the support, I mean, then to find the probability of those particular values, we would add up the probabilities. And in some regards, the definite integral is a summing up of the probabilities here. It's accumulating the probabilities. Okay, so let's do an example. Let's say we have this PDF that's constant times sine of x. We're first going to find c if the x is defined between 0 and pi. And then we'll find the probability between pi over 6 and 2 pi over 3. We'll find the mean, and we'll find the variance. All right, so first find the c. To find the c, we know that when we integrate over the support for our PDF, we have to get 1. Well, antiderivative for sine is negative cosine. Plug in, We get 2c is equal to 1, so c has to be a half. So not a big deal there. Using the third property of being a probability density function, the probability that x is in between these two values is the integral of the PDF over that interval. Antiderivative here, plug in our endpoints, do some simplifying, and get root 3 plus 1 over 4 as our probability. Okay. So again, if we're looking for probabilities that were in between two values, we're going to integrate our function over the interval. Integrate our probability density function, or PDF we call it that in that case. All right, how about the mean? Well, just like we compute expected value in discrete case, we're going to compute expected value in the continuous case in the same way. We'll take our x, multiply by our PDF, and integrate over the entire support. So it's x times f of x, integrate this time instead of summate, take a summation. All right, well, this is going to require integration by parts, so we'll let u equal the x, dv be sine x. We'll just pop the 1/2 out in front. Here's your du and your v. Here's what you get after you apply the integration by parts formula. Remember, it's u times v minus the integral of v du. That's why it's a plus sign, because there's a minus there with the v as well. Anti-differentiate cosine. Plug in our values, we get pi over 2. You could do the same thing with expected value of x squared. Multiply by x squared here. This requires 2 integration by parts. Applying the integration by parts formula twice. I didn't show it here, but you should make sure that you understand and know how to do integration by parts to be able to solve some of these integrals. They will pop up. Plug in our endpoints, we get pi squared minus 4 over 2. That's for expected value of x squared. Now, just like before, we have to subtract off the mean squared. When we do that, we get pi squared minus 8 over 4. So this gives you a brief introduction into what we mean by continuous variables and how to calculate probabilities and mean and variance for continuous variables. So in class, we'll talk about finding moment generating functions and doing some more example problems.